Yes.
Dankjewel.
Succesvol waren.
Ja, dankjewel.
Ik ga eerst even de sessie openen en dan krijg je
Ja, dat is prima. Er is die microfoon staan.
Is
Ik zal die even aan.
Ja. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you all to the public defense of Mathias Michielsen. Mathias has presented to the faculty his PhD thesis on the topic Forward Seismic Modeling of B-type stars, in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy and astrophysics. He shall now publicly defend his PhD thesis. Mathias, you're invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. After the presentation, I will present to you the members of the PhD committee. And after the members of the PhD committee have asked their questions, there will also, since this is public defense, there will also be the opportunity for you to ask questions to Mathias. With that, I now give the floor to Mathias. Please go ahead.
All right, so okay, the sound is on. Goed. Hallo, welkom allemaal op deze doctoraatsverlening. Ik ga de presentatie in het Engels geven. Maar stel dat je zegt van, goh ja, Engels dat is niet mijn eerste taal, dat is een beetje moeilijk allemaal. Ik zou toch nog graag eens in het Nederlands ook horen. Aarzel dan niet om achteraf van mij te komen vragen en dan geef ik gerust een extra woordje aan. Alright, so continuing in English now. I will first start to explain some of the concepts to help you understand what all these words in my title actually mean, right? And to do this, I will start with the easiest one. What is a star? And if we don't bother too much with details and we just make some simplifications, then I can use a quote of a very wise individual to say that all stars are actually just burning balls of gas. However, not every burning ball of gas is the same. And if we take the surface temperature of stars and we sort them along their surface temperature, we see that we get stars that are very, very hot at their surface, and we have stars that are cooler at their surface. And in general, the more massive stars are hotter at their surface, and the less massive stars, the smaller ones, are cooler at their surface. Then the naming of these stars is divided in spectral types. So that's like the names that are underneath there, the O, B, A, right? Is like a historical way that astronomers have named these stars, and how they ended up with these names, I don't know. But there are some easy sentences to remember, like this naming scheme. And my favorite is, one bad afternoon, 5 goats kicked me. And this might not be the sentence that most astronomers were expecting, but it's still the one I'm going with today. In my title, I said I was going to look at B-type stars. So you see these B-type stars, they're much more massive and much hotter than our sun, because our sun is only a G-type star, so much smaller. Now, if I take the temperature of our stars and I put that on an x-axis, right, and then add another dimension. So on the y-axis, I will put the luminosity of the star, so how much light comes from the star. Then we end up with such a diagram. And there are a lot of stars here, and astronomers use this diagram very often. It's called the Hertzsprung-Russell diagram, and it tells us a lot about the different types of stars. So the stars that I will be looking at today are the ones on the diagram that we have here. That's called the main sequence. And this main sequence stars are stars that are burning hydrogen into helium in their stellar core. So after this phase, they will continue on and become giants or supergiants. And if they're not that massive, then they will become white dwarfs. Or if they're very massive stars, they will go on and become supernovae and end up as neutron stars or black holes. And these are all very interesting things to look at, but today I will focus on the main sequence and this phase, because that's also like the phase that takes the longest in the stellar life. All right. So now going back to the B-type stars that I was looking at, they're very hot at their surface, and they have masses that typically range from 3 to 16 times the mass of our sun. So they're actually quite massive as well. So the B in B-type stars, you can think of it as it stands for big stars. Not the actual name, but it's a good reminder for during this talk. Now, if I would represent a B-type star in a very simple schematic way, then I'm going to take this green circle and say, okay, well, this is our B-type star. And to explain to you what the internal structure of this star is, I will make an analogy. Right? So imagine you're getting a bit hungry, you think, oh, I could use some proteins, I'm going to cook an egg. So you take a pot of water, you put it on fire, and then you add heat to this water, right? So you have a source of energy, the fire, that will heat up your water. In a star, you will also have a source of energy in the center, and this is the nuclear fusion. So this is the hydrogen that gets fused into helium in the stellar core. So as a quick note, nothing on this image is to scale, neither the sizes of the internal structure nor the cooking pots next to it. All right, but so you have nuclear fusion happening inside the stellar core, and this energy that gets generated, it's a lot of energy, especially in massive stars where you have very much mass in the star that all gets like pulled together through gravity. The center of the star will get very hot, will get a very high pressure, so a lot of nuclear fusion will happen, a lot of energy gets generated, and this all needs to be transported outwards. And this can happen through just like radiation or through conduction, but at some point there is too much energy to be transported, and this needs to be transported by a more efficient mechanism. So we will start to have convection in our pot of water. Our water will start to boil. We will have fluids elements, so hot water that will rise up, and hot water that will sink down. And in our star, we will also have this convective region in our star where all the material that is there gets mixed to transport energy efficiently outwards. Okay, so far so good. But we have, if you think of our boiling pot of water, a surface layer actually. And if you look at the pot of water, you see like where does the water end, where does the air begin, where is like this boundary exactly. And in our star, it's also not necessarily a very clear-cut region where this transition takes place. So we have a boundary layer actually, where you can have like blocks of material that just go outside of the regular convective zone and also mix the material that is present there. Okay, so just to summarize, in our star, in the center, we have a convective core in gray. We have a radiative envelope where no convection is happening in green outside of that. And in between those two regions, we have like the mixing region, the convective boundary mixing region, or CBM, that is there. And such a region is actually very important for the life of our star, because if there is extra convection and the convective zone of our star is larger, then there is a larger region where all the material gets mixed. And if you think about it, if more material gets mixed, then all the hydrogen that is in this newly convective region will also be brought to the stellar center where the nuclear synthesis is happening. So we will just bring fresh hydrogen to the stellar core, and this will be additional fuel that the star can use during its life. So it will have more fuel to burn during its sequence lifetime, and therefore, since it has more fuel, it will have a different evolution than a star that would not have this. And also, it will have a much longer lifespan. So, in this figure, I have again shown like the temperature on the x-axis and on the y-axis the luminosity. So it's again this Hertz from Russell diagram that we had earlier. And in the bottom left corner, I have put a star which has 4 solar masses and it's on the main sequence. And we're going to simulate the main sequence evolution of this star. Now, the color of this star will represent the age of the star. So the dark star will be very young, and the lighter it gets, the older it gets. And you will see that there are actually, if I start the simulation, there are 2 tracks that are going on at the same time, and one will have convective boundary mixing, and the other won't have it. So the track that's the highest one, the one on top, will have convective boundary mixing, where you have this additional material that gets mixed, so more fuel for our star. So you'll see that it appears much more luminous, and it will also evolve much longer. So the one star will already stop its main sequence. Its main sequence will end much sooner, right? So the one that has more material available will continue evolving on the sequence for a longer time. All right, good. So next up, if we want to simulate these stars, as I had just done now, then it's a bit cumbersome to take a full 3D star and evolve that through the whole evolution, because this evolution is millions or billions of years. And if we simulate a star in 3 dimensions and have all the proper descriptions for these processes, then it takes a lot of computation power. So what we often do is we try and make some simplifications. So if we make the simplification and say that our star is spherically symmetric, so it's the same in every direction, then I can take this arrow that I have drawn here. So I take the little circle in the center of our star and draw an arrow towards the surface. And I can actually draw this arrow in any direction, and it will always be the same, because it's the same in any direction. Even not only the ones that I've drawn here, but even the ones that would come out of the projection as well, right? If you think of it in 3 dimensions. So since each line is the same, then we don't need to simulate the whole star. We can just simulate what happens along one of those lines. And then I show something like this, which is called a mixing diagram. So on the x-axis, from left to right, we have from the inside towards outside of our star. And the colors that you see are, again, these mixing properties that are happening. But the higher they are, the more mixing that is taking place. So the blue region, the boundary mixing region, and the gray region, the core mixing region, they are very high, so they have a lot of mixing, whereas in the envelope, not that much mixing is going on. Also, this axis is in logarithmic scale, which means that if you have a value of 10, it's not 10 times higher than a value of 1. It means that there are 10 zeros behind your value, right? So it's a billion times higher than a value of 1. Okay? So it's really a very, very large difference between the mixing in the core and the mixing in the envelope. All right, so if we zoom in a bit on this boundary mixing region, so the blue region, then we can actually have different prescriptions to say, like, what is going on exactly, what is happening there. And we can say, like, oh, well, 2 of the commonly used prescriptions in astronomy is either we say, okay, well, we just have a constant amount of mixing that is happening in this region, and we drop it after that region, and that's it. Or we can say, well, we have like a gradually decaying amount of mixing where it's higher near the core but lower further outwards. Right? So these are different ways to like prescribe this, and different ways to put it in stellar evolution codes. Now, how can we actually see inside the star? Because I've told you, like, oh, this is what is happening in the star, and these are different prescriptions, but how can we see the processes that are going on and get an idea about which of these things is actually like a better way to describe our stellar models? Because, well, if you would look at, for example, the Earth, you can't look through the surface layer of the Earth. In the same sense, you can't look through the surface layers of a star to see what's happening in the very core. Now, a very good way to do this is through the use of astroseismology. Astroseismology is the study of stellar pulsations. So you have regions in your star where you have areas that are expanding. So the regions in blue, for example, they expanded it, and that surface is coming towards us. And the regions in red here are contracting and going away from you. So, and yeah, then the regions in the white in the middle, they are called nodes, and that are regions where the surface doesn't move, actually. So these regions are static, and the regions around it are making these motions. Now, we then have 3, that's so-called quantum numbers to describe these, such an oscillation, right? So we have L, which is the amount of these nodes, so the amount of these white lines on the stellar surface. And we have M, which is the amount of such nodes that are lines that go through the axis of symmetry. So in this case, for example, on the right, we see 3 of these white lines, so L is 3, and M is 2, because 2 of them are going through the pole, and the third one is on the equator. All right, then the last thing that's there is M, the radial order, which is the amount of these nodes that are happening radially inside the star. So from the core of the star towards the surface. And to get a better look at this, I'm going to take a star, cut a piece out of it, and show you this image. So this is a representation of such a pulsation happening in a star, where you can see the motions going on in not necessarily real time, but you can see the evolution going on. All right. So in this case, again, we have the surface nodes that are present. We have like one of them that is through a pole, and then we have some of these regions as well, these nodes that are inside the star radially. So that is how we describe like what such oscillations look like and how we can describe them mathematically. Now, there are actually two types of pulsations. So we have pressure modes or P modes, which are sound waves actually. So the waves that I'm using to talk to you guys, so the air that is compressed and expands afterwards to get what I'm saying to your ears, is a sound wave. The pressure is the restoring force, and we have these kinds of waves as well in the interiors of stars. And these types of waves are very sensitive to the outer layers of stars. On the other hand, we have gravity modes or G modes, where the buoyancy is the restoring force. And these modes are very sensitive to the deep interior of our stars. Now, for the remainder of this talk, I will be focusing on the gravity modes, so the G modes, because those are the modes that are occurring in the type of pulsating star, slowly pulsating B stars, which are stars that I will be looking at later. All right, so these gravity modes have a special property, and it is that they cannot propagate through these convective zones. So if I again show these simplified representations of what a star looks like with its convection zones, we have the high mass star on the right, which I already showed to you before, where you have a convective core, right? Then a boundary layer, and then a very large radiative envelope. On the other hand, if you look at a star that is much lower mass, for example, our sun is such a star, then the situation is reversed, and you will have the convection zone at the outer layers, and you will only have the radiative layer inside of the star. Now, since gravity modes cannot propagate through convective zones, in the low mass star, these will be trapped in the center, right? So these lines that are shown there is like the propagation of a mode through the stellar interior. And we see that it doesn't reach the surface. So in these low mass stars, you would not be able to see the gravity modes. However, in a high mass star, these modes are, they're trapped, let's say, outside of the stellar core, but they do reach the surface. So in that sense, you can observe them, and you can look at their properties and see what we can learn from them. Now, since these modes cannot propagate in the central convective zone, they are very sensitive to the size of this zone as well. So because if this zone is larger or smaller, then that directly influences the region where this mode can propagate, yes or no. So it will have a fairly significant impact on the mode properties. Okay. But, okay, this is how these oscillations are present in stars and how we describe them, but we want also to observe them, of course. So how can we do this? If we take a telescope and we look at a star, and we have a very, very precise measurement of the amount of light that we get from the star, then we see that there are variations in the brightness of the star. Because if the star has regions that are expanding, then they give a bit more light, and if they are contracting, they give a bit of less light. And you can see this evolving through time. If you take a lot of measurements in consecutive after one another, you see that the amount of light that you get, so the brightness increases and decreases periodically. And in a star, you will actually have a combination of a lot of pulsations happening at the same time. So it's not one of these pulsations with a certain L, M, and N that is happening, but there are all of them that are going on at the same time. And you will get something, well, this is a simple representation, but you will get a combination of different of these oscillations. Now, if you want then to unravel the signal and say, well, we have this combination of our signals, but we want to say, well, which are the individual pulsations, then we have a mathematical technique called a Fourier transform, where we can get the pulsation spectrum of our star. So on the x-axis now, we have the frequency of a certain oscillation mode, and then the height on the y-axis is the amplitude. Right? So the larger your pulsation, the higher the amplitude, and well, the faster it happens, the higher the frequency. Okay. Now, this was a very simple example where I just put two oscillations together and then said, okay, well, now we're going to do a Fourier transform and see what it looks like. But if we look at an actual star that is observed, then we have a picture that looks like this. So the gray line that you have there is an actual observation of the star. And you see that there are a lot more pulsations going on because there is a lot of variability in this light curve. The lines in red that you see, those are the Fourier transform where we have the pulsation spectrum what I will do here is I will just flip it around, and instead of frequency on the x-axis, I will put periods there. So this just means that instead of saying this pulsation happens this many times per day, I will say this pulsation takes this many days to do one full cycle. All right, so when you have these pulsation spectra of our gravity modes, then we can go and we can look for pulsation patterns. So in this case, if I would indicate certain of these modes that we see here, well, the pulsation modes that are observed are indicated by these blue lines. And if I indicate some of them in yellow, then we see that the pattern starts to occur. And we're searching for patterns where the L and the M values of our oscillation are the same, but where the N values are consecutive. So if they're consecutive in radial order, so in N number, then we will see that these differences between two oscillations are approximately the same. So this distance between two frequencies will be more or less constant. Now, we use this to make a new type of figure, which is a period spacing diagram. So we have the pulsation spectrum in the top panel, and on the bottom panel we will have the pulsation spectrum, the pulsation, period spacing diagram, sorry. So the period spacing diagram is on the bottom, and there on the x-axis is just the period of our modes. On the y-axis, we will have these differences between two consecutive modes, right? My projector is doing something weird. But so the differences between two consecutive modes are the values of our period spacing on the y-axis. And we can learn a lot from these pulsation patterns, because if you would have a star that is very young, so it's chemically homogeneous, there is not a lot of nuclear fusion has happened yet. So throughout the star, the material is everywhere approximately the same, and we have no rotation. Then we have this black line, and we see that it's just a constant value. It doesn't deviate a lot from its value. Right? If you introduce rotation, however, then we will get the lines that are a bit lighter. So we see that then with increasing rotation, there starts to occur a tilt in this pattern. And the more this pattern is tilted, the higher rotation will be. So this tells you a lot about your star. Now, if we don't only look at the very young star, but we also allow our star to evolve a bit and become older, then we will see that it's no longer a straight line, but that we will have dips in this pattern. So we will see that these dips start to occur because of the stellar structure that will start to form. And the older the star gets, the more pronounced these dips will be and the more of them you will observe. Okay, so far so good. I'm going to introduce one more concept, which is called a Brunt-Väisälä frequency. So this Brunt-Väisälä frequency, you can think of it as a frequency that is a value throughout your star, and it determines if your gravity modes can propagate through that region or not. So these gravity modes can only propagate in regions where their frequency is smaller than the frequency of the Brunt-Väisälä. So, for example, if I draw these two lines here, one has a higher frequency, so it can only propagate in a smaller region than the one that's below it, where the frequency is a bit larger. The frequency is lower, but the propagation cavity is larger because of the shape of our Brunt-Väisälä frequency. So this is actually the thing that determines a lot of the properties of our gravity modes. Now, this Brunt-Väisälä frequency is made up out of two components. One is the thermal structure, so like how temperature behaves in our star, and the other is the chemical gradient that we have in our star, which will be determined by the mixing profile. Because, well, if our material is mixed and we have a lot of mixing going on, then, well, there is no chemical gradient because, well, the difference in material that you would have just gets mixed out, right? But further outwards, where you don't have this mixing, then you can have a chemical gradient that starts to develop. Especially in these B-type stars, where during their main sequence evolution, your convective core will start to shrink during the evolution. And if it shrinks, then it will leave behind this chemical gradient, because this convection zone becomes smaller and smaller over time. Okay. Now, since we have these two components to investigate, I will first take a look at the mixing profiles that we have. So these are two mixing profiles that you saw earlier during the talk already. And here I have used just one free parameter to describe this region, right? So the first one, we just have this step-like function where you have a constant amount of mixing for a certain distance, and that's it. In the second one, you will have this decaying value where there is another, just a single parameter determining how this decay happens and how fast it happens. What I did during my PhD was I thought, well, wouldn't it be nice if we combine both and have both of them together and say, well, we have now a prescription with two free parameters. But when we use this prescription and we set one of those to 0, then we end up with what we had before. So for example, in this case with 2, if I put alpha to 0, then I will just end up with the one where we just have an f. And if I put both of them to 0, then we will only have the core boundary, then we will only have the core mixing and no convective boundary mixing at all. And in that sense, you can compare different prescriptions with more or less free parameters to one another. So that's it for the mixing profiles. Now, if you look at the other thing that we were going to investigate, the thermal structures, then I have a figure where a lot is going on, but the bottom panel you already know, because there it's again the mixing profile that's shown. And the red line that's shown on top are these two components of the Bruin-Väisälä frequency. Right? So you have the solid line and the dotted line, they're both the components of the Bruin-Väisälä frequency. Now, the panel on top of that is the temperature gradients that are shown there. So you have the dotted lines, which are the adiabatic and the radiative gradients, and you have in red the temperature gradients, the actual temperature gradients that is present in your star. Now, what is happening here is your temperature gradients follows the adiabatic gradients very closely inside your stellar stellar core convective zone, so in the gray region. So what this means is that if your flow there is happening adiabatically, that your blocks of material cannot exchange heat with their surroundings. But once they pass the core region and they get into this blue region, the convective boundary mixing zone, then the temperature gradient will no longer be adiabatic, but it will become radiative. So there, it can exchange heat with its surroundings. So that's a very important difference. Now, this is one way to describe the temperature gradients happening in this CBM zone. I've implemented another way where I didn't just switch the gradients at the edge of the core region, but where I based this on a Peclet number. Now, what this Peclet number specifically is, you can think of it as a measure of how adiabatic your flow is, right? So based on this Peclet number that you can calculate from your stellar properties, you get an idea of, is my mixing that is happening adiabatic or not? And if I approach it in such a way, then I see that the mixing also in this convective boundary mixing region is adiabatic for a certain area, right? So you see that with this red line here, it stays adiabatic for a little bit longer and then only makes a gradual transition towards this radiative gradient. Area where our material gets transported without being able to exchange heat with its surroundings. Now, why is this important and why does this matter for what we're looking at? If we now look again at our Bruin-Väisälä frequencies in the panels below, then we see that on the left side, this Bruin-Väisälä frequency starts to become different from 0 right outside of the convective core. So this whole convective boundary mixing region has a value of the Bruin-Väisälä frequency that is different from 0. And if you remember, gravity modes can only propagate in a region if their frequency is smaller than the Bruin-Väisälä frequency. So this means that there are gravity modes that can propagate through this region. On the other hand, in this Peclet-based description, we see that this Bruin-Väisälä frequency stays 0 for a bit longer. So that means that these gravity modes can no longer propagate in that region, and they have now a smaller propagation cavity, which is something that will directly impact their properties. Now, how this impacts their properties, I'm going to add one more panel to this figure. So in this bottom panel, I show the mode inertia, but you can think of this as how sensitive a mode is to a certain region. Right? So you see that on the left-hand side, you have this mode indicated in black that has a very high mode inertia, whereas on the right-hand side, this mode inertia is much lower in this region near the core. And this difference is just because we changed the temperature gradients. Now, this mode trapping that is happening here. So that's what we call it, if a mode has a very peaked mode inertia in this region. So this mode trapping is something that you see in this period spacing patterns that we had earlier, right? So if we have this period spacing patterns again, then we see that these dips in the structure are these modes that experience this trapping. And if we change the temperature gradients, that's what we do here when we go from the red to the blue lines, then we see that these dips occur at different modes. So there are still dips in the pattern, but they are just shifted a bit. And this is all because of the change in the temperature gradient. Okay. Now, this change and this shift in these dips is something that is large enough so that we should be able to see it when we look at actual observations. So we should be able to tell the difference. So then we of course want to compare this to observations. Right? We want to see, okay, what is now happening in an actual star if we take a lot of models, we compute a lot of theoretical models, and we compare it with observations. So to do this, we need to establish a modeling methodology. We need to make certain decisions in how we're going to approach this problem. So to start off, I compute a lot of models, right, where I vary a few parameters. So I vary the mass, I vary the age, the chemical composition of our star, and the mixing properties. So this is both the amount of mixing that is present in the envelope, so in the green region, and the amount of mixing that is happening in the blue region, the convective boundary mixing region, right? And then this can be with like with one free parameter or two free parameters, or I can just leave it out as well and then have no free parameters for this convective boundary mixing region. Okay, so we have our theoretical models, and we want to compare them to the observations. And one thing that we could do is we can say, well, let's assume that our theory is perfect, nothing to worry about. We can just compare all of these things. Sadly enough, we cannot do this because our theoretical models also have uncertainties in them. So we want to take the correlations and the uncertainties of our theoretical models into account and not just look at the observational uncertainties. We want to look at both the observational and the theoretical uncertainties and see how these affect our modeling. Okay, and we do this through the use of the Mahalanobis distance. So the Mahalanobis distance is a mathematical merit function, we call it, that is used to take these things into account when we do our stellar modeling. Right. So that's one important aspect of our methodology. The other important aspect is that I said that we would have different prescriptions with a different amount of free parameters. Right? So we had 2 free parameters, or 1, or even 0 for our convective boundary mixing. So what we will do there is we will use the Akaike information criterion, which is another mathematical tool, where we would balance the model complexity to the fit quality. So we will reward the fit quality of our theoretical models, and we will penalize the additional model complexity, right? Because it's always easier to fit things, to fit observations when you have more free parameters to play around with. Okay, so our methodology is established. Now, these are 2 observed slowly pulsating B-type stars. So these are 2 actual observations of stars, and we're going to try to model these. Now, there are 2 things that you can immediately see already from these patterns. If you paid attention earlier, you see that they are tilted. So these stars will be rotating a little bit, and you see that there are dips in these patterns. So there will be some structure that is already present. So these stars will have been on their sequence for a while, and they will have some evolution that has happened already. So the one on the left is a single star, and it has 36 observed pulsation units in this pattern. And the other on the right is a star that is in a binary, and it has a lot fewer modes. Well, a lot fewer. It has 22 modes that are observed in this pulsation pattern. All right. So I'm going to start off looking at the single star and take this observed pattern, have it as the black line here, and I have put 3 theoretical models on top of this. And these are 3 theoretical models that explain the data pretty good. We see the ones in blue and red, and they are the models with 6 free parameters. Right? So here we have all this boundary mixing that is happening with the most free parameters that I put in my models. And I have put next to them in purple the one where there is no convective boundary mixing at all. So that's 2 less free parameters. And well, by eye, you can see, well, the ones with the extra free parameters, they do a better job at reproducing these observations. Yeah, it looks to match better. And if you use a mathematical tool that does not take into account all these theoretical uncertainties, then you will see, well, yes, indeed, that's the better thing. However, if we use our Mahalo modus distances and we do take all these things into account, and we use our Akaike information criterion, our scale, and we put the model complexity on the one hand and the fit quality on the other hand, then we see that this model complexity outweighs the fit quality. So we see that our model with 4 free parameters is statistically preferred in this case, even though it looks much less good than the others. Now, the main reason for this is that we have very large theoretical uncertainties. So these bars that I show on the bottom left here are the maximal uncertainty that we have on these different patterns. And the one in black for the observations, I've multiplied it by 10 times already, because otherwise it would be too small and you would hardly see it. Right? So from this you see that the model uncertainties are much larger than the observational uncertainties. Now, we can go on and look at our other star. Here again, I have shown, in this case, in purple again, the model without any convective boundary mixing, and then in blue and red, the models with 5 free parameters. And I show also the uncertainties there. If I do here the same exercise and put the penalty for the complexity next to the increase in fit quality, then we see that this balances out. And it's actually, yeah, statistically speaking, you say, well, they're equally good because you gain a lot in fit quality, but you also optimize for that a bit, but it's about the same factor. So statistically speaking, these models are just as well to describe what is happening in our star. Okay, so now to come back to the 2 things that we were investigating. So we were investigating temperature gradients, right? If I look at these 2 stars and say, okay, well, we have this radiative and this Peclet temperature gradient, right? For our star on the left here, I find that if I assume that there is convective boundary mixing present, and I say, okay, well, let's just assume that it's there, let's look at which temperature gradient works best. We see that the radiative temperature gradient is the one that is doing the better job. If we look at the other model, on the right, the other star, I mean, on the right, and we do the same exercise, then we actually see that, well, we can't distinguish between these 2. Well, it could be one, could be the other. In a sense, the Peclet prescription here does a little bit of a better job, but it's not good enough so that it's statistically significant. So it's only a little bit better, but not enough of a better job. Now, one thing that you can take, well, that I think is the cause of this is that on the left-hand side, we have a lot longer pattern that we have in our observations. So there we have 36 observed modes, whereas on the right, we only had 22 observed modes. So these extra modes, so this longer observed pattern, means that we have more probing power in our star, because we have more modes that are probing different parts of our star, and that can propagate through a little bit more or a little bit less of the star. In that sense, we have more probing power, so that we need these more modes to be able to actually tell the difference between these 2. All right, so that's mixing profile on the one hand. Then the other thing we were, that was the temperature gradient on the one hand, but the other thing we were going to look at was the mixing profile. And the mixing profile, as I show here, these are the 4 practically descriptions that we looked at, right? So nothing at all, then 1 free parameter, and then either the step or the exponential decay, or then the 2 free parameters and the combination of both. If we look at this for the star on the left, then remember we had that the model complexity outweighed the fit quality. So we can just say, well, actually, statistically speaking, we would want the model where there's no convective boundary mixing at all present. In the other case, we had that they balanced out. But in that case, we can still say, like, well, this one with the step function does not perform as good as the other, so we can rule that one out. One thing that I think here might be the cause between this discrepancy between our 2 stars is that on the left, where the model complexity outweighed the fit quality, we had very large error bars, which are the cause for this, right? Because there our model just says, well, if you have such large error bars, then, well, why would you use 6 free parameters if you can just as well do it with 4? Because everything falls within your error bars anyway, right? Don't bother with the extra parameters, it works fine. On the other side, where this model complexity and the fit quality balance out a bit more, we see that the theoretical uncertainties are a little bit smaller. They're not a super, well, not a very large amount smaller, but they're a bit smaller. And I think this is one of the causes that indicates that, well, what we want to do actually is to reduce our theoretical error bars so that we can, that we can get models that are describing our observations better, probably with additional complexity, but in such a way that the additional complexity does not get, does not outweigh the increase in fit quality. Okay, so to summarize all of this, we had the thermal structure in our star that has a very large influence on the mode trapping, right? So the dips in our pattern get shifted significantly just because our thermal structure changes. And we have a need of long period spacing patterns to tell this difference observationally. Because, well, the difference is significant, but if you have observations that you need to model, there are a lot of things that are going on in there, and there are a lot of things that we need to take care of. So we need these long patterns to be able to have the probing power to tell the difference. But overall, I would say that we have very large theoretical uncertainties that actually are dominant in our modeling process. They're much larger than the observational uncertainties, and this might be an indication that we're reaching the limits of our one-dimensional approximations. Because remember, in the beginning, I said, well, let's take a start, assume it's spherically symmetric, so the lines that we draw are the same in each direction, so we just simulate one line. But in essence, convection that we're studying here is a three-dimensional process. So yeah, there are a lot of assumptions that go on in there, and this might be an indication that we would actually need to go to a coupling between three-dimensional models and one-dimensional models as something that we can do towards the future, where we take the structure of a three-dimensional model, use that to evolve a model in one dimension, and then couple that structure back to the three-dimensional model that then gives an update, and in such a way couple back and forth between the two to have a more consistent stellar evolution throughout our whole instruments. All right, and with that, I'm going to round off, and I'll take any questions.
Yes, thank you very much for this nice and lively presentation. So, ladies and gentlemen, we now move towards the second part of the subject PhD defense. Now I need a microphone. First of all, I would like to present you the members of this examination committee. And I'm going to start with Professor Mathias from the Institute of Astronomy, University of Germany, is the promoting contest. Then we also have two external members, and one of them is Professor Rich Townsend from the University of Wisconsin at Madison. And yes, there we can see him in the United States of America. The second external member of this examination committee is Professor Achim Weiss from the Max-Planck Institute für Astrophysik in Garching in Germany. And then we have also Professor Tim von Osterhagen, who is here with us, who is a professor at the Department of Mathematics at the University of Leuven, and then also Dr. Dominic Bowman from the Institute of Astronomy at the University of Leuven. My name is Adams. I am in the Quantum State Physics Division in the Department of Physics and Astronomy. It's my pleasure and honor to chair this session. I should also say that this PhD process goes in two steps. We've had the first meeting back in September, where we had a close meeting with the entire examination committee, and where we had a very thorough grilling of the candidates. And that went very successfully, so today it is allowed to use public defense. And now we will come to the question session. First of all, I will give the word to the members of the examination committee, and then after that, I will also give you the public the opportunity to ask questions. And do so in the same order as we used during post defense. And therefore, I would like to call on Rich Townsend to ask his questions first. Rich, are you with us?
Yep.
Go ahead.
Okay, so Mathias, thank you very much for a beautiful talk. I think you covered some very complex science.
Sorry, the audio does seem to come. All right, can you try again?
Okay, can you hear me now?
Yes, okay, much better, thank you.
Okay, so I really enjoyed your talk. You gave a lovely, accessible account of quite a complex piece of science, and I very much hope that I can get my hands on a recording so I can show it to my students.
You certainly can. It will be on YouTube for as long as YouTube exists, I think. So, yeah.
Okay, great. So early on in your talk, you mentioned that G-modes can't penetrate convection zones. But I know some more massive stars have thin convection zones near their surface, and yet we still see G-modes at the surface of these stars. So can you briefly explain how that's possible?
I made a bit of a simplification there, yes. G-modes will have an evanescent behavior in these regions. So that means that if you have a G-mode and it will have a certain amplitude, then it will decrease rapidly in this convective zone. And if you have a very large convective zone, then yeah, it will just stop almost immediately. But if your convective zone is very small, then it can still reach the other side of this zone, even though it has a bit of an evanescent behavior then in that region.
Okay, thank you. On to observations. In your light curve for KIC 493, I'm not going to say the rest of it,
Yeah, okay.
there were some gaps in the light curve. What causes these gaps?
Well, there can be gaps in such a light curve just because of instrumentation effects. If your telescope is pointing towards a certain star and well, it needs to adjust its pointing, or then you can have these short interruptions. There can also be like mechanical failures at some point, which are all things that can introduce such small gaps.
Okay, so
you need to keep in mind that this was data from Kepler, which is a very good space telescope that pointed at a certain field in the sky for 4 years in 4 years in a row. But well, the Earth also moves around the sun and all these things, so yeah, these pointings need to be adjusted, and then you have instrumental effects that come into play there.
So do these gaps have a big effect on the Fourier transform, or are they relatively unimportant?
These gaps will have some effect on the Fourier transform, right? But in this sense, you have very nice data for a very long period of time, and then you have a relatively small gap, and then again a very long time of very nice data. And in such a case, then the impact will be relatively limited. If you would have things like, for example, ground-based observations, and you would point at the star and observe it during the night, but then during the day you can't observe. So you would have each day like a gap that's as long as your observations. Then you would have a very large effect of this, right? And you would just have a lot of signal that's there just because of your periodicity of 1 day, where you have like the Earth rotating around itself and you only being able to observe half of the time. Whereas, with space telescopes, that's much better in that space.
Okay, thank you. Moving on now to your period spacing patterns for KIC 776. Again, I'm not going to say the rest of it. The fits between the observations and the different models are pretty good towards longer periods. But at short periods, around 0.9 days, none of the models seem to reproduce the observations well. And could you say a little bit about that disagreement and what it tells us about our models for the stellar structure? What part of the stellar structure is causing that discrepancy, do you think?
Yeah, so what is happening there is that you have modes that are at lower periods. So then I always need to think if these are the higher or the lower radial order modes. But modes with different radial orders, they probe different parts in our star. So yeah, if you probe it depends a bit on which part of your star that you're probing, how sensitive you are to certain effects that are going on, right? Now let me think. If you have a higher radial order, that means that you have a lower frequency, so a higher period. So the lower period ones will be the lower radial order modes, right? So yeah, these low radial order modes will their sensitivity will be a bit more outwards than the higher radial order modes, which will be more sensitive towards a very, very near correlation. So the differences that you see there is because of this difference in where our modes are sensitive to. And another effect that is also in play there, I think, is that our observational errors are largest at the high period end. But if I am not mistaken, the theoretical errors were larger at the low period end. So that's the reason why these modes tend to match a bit worse, because our theoretical uncertainties there are quite a bit larger.
So could I get you to speculate about what physics maybe is missing from the models that makes the match not very good at the low period end?
That's a difficult question because there's quite a bit of physics that is missing or not super well. I mean, looking at where stellar models are right now, they're pretty good if you just think about what we're actually observing and trying to model, but we're still far away from reality. Right? I guess since they're the lower period ends and they're more sensitive towards the outer layers than the other ones, then the missing things there are probably in the outer parts of our star. Which could be things like, for example, let's say iron opacity bump in our models, where opacity is something that is notoriously difficult to calculate and include in models, and where we know that there are still a lot of shortcomings present. So that might be a candidate for that.
Okay, thank you. That was a very nice answer. I think that concludes my questioning.
Okay. All right. Then we can move to Achim. Achim, are you still with us?
Right, can we try that again?
Achim, it's your turn now for questions.
Yeah, okay, there I am. Yeah. Okay, Matthias, you can hear me clearly?
Yes, yeah.
Okay, thank you very much. You started with very broad information about stars, and then you became more and more complex. I suppose you lost a few of the audience in that way. I will try to do the same. I start with two questions which are really not directly related to your thesis, but may have come up for the audience. The first one is, you mentioned that at the core of these stars, there is hydrogen being fused to helium. How do we know that actually?
Well, most of the material in our universe is hydrogen, right? So that's the most prevalent element around us. And if we look at like the composition of stars, we also see that then, of course, there is a lot of hydrogen present in these stars. If we look at nucleosynthesis processes, and if you look at when certain elements would start to have nuclear fusion and fuse into heavier elements, then the temperature that you need for hydrogen to fuse into helium is lower than for example, helium to fuse into something else. So since your temperature and pressure need to be lower, then you will reach the conditions for these fusion processes much sooner than for the other elements. And that's why, well, you will have this hydrogen fusion occurring before the others will happen.
Yeah, thank you very much. That's a very scientific answer, yeah, in terms of cell evolution theory. I was thinking more of a direct experimental evidence that we have since the 60s.
Observed evidence or experimental evidence?
Experimental evidence.
Experimental evidence.
In laboratories on Earth.
On Earth. Well, yeah, there are some tests I'm aware of with nuclear fusion reactors where people are trying to generate energy by fusing certain elements into heavier elements, but I'm not sure if that's what you were alluding to.
No. It's much easier. I'm sorry, I'm confusing you because you don't believe that the question is so easy. No, I was thinking of the neutrino experiments, the solar neutrinos. Yeah.
Oh.
The solar neutrinos are direct evidence that something is going on. Okay, I'm sorry. I thought it would be easy because we have. Yeah, the reason is that seismology is not the only way to look inside stars. Yeah, we have a few others, and one is the neutrino experiments measuring solar neutrinos that come directly from the burning core. Yeah. Okay, good. Another question. You showed that evolutionary path of the 4 solar mass stars. Yeah.
Yes.
Yeah, you remember up to the end of the main sequence. So when the end of the fusion in the center is happening. But maybe your audience has wondered what happened afterwards. Are these stars dying there, or what is happening there? Maybe you explain that briefly to the audience. What's happening afterwards, where these stars move in your Hertzsprung-Russell diagram.
Yeah. Well, that's I mentioned briefly in the beginning where I showed this Hertzsprung-Russell diagram where we had our main sequence, and this main sequence evolution that I showed then later is just a small part across this main sequence, right? And then depending on what type of star you're looking at, how massive it is, it will go on and then become a red giant or a supergiant, right? And then from that stage onwards, evolve further to either become like a white dwarf or go supernova if it's a massive star. So yeah, the life of a star certainly doesn't end at the end of the main sequence, but the main sequence is, let's say, 90% in time of of the life of your star. And then the phases after that happen much quicker. So for example, for this 4th solar mass star that we would have, it would have its main sequence, it would fuse all the hydrogen in its core into helium, and then once the hydrogen has run out, then there's no more fuel. So yeah, this nuclear reactor will just stop working. And then our star will start to contract again because we have gravity, and then this further contraction happens where you will have an increase in pressure and temperature because of that. And then you can have 2 things that happen. One is you will have hydrogen that will start to burn outside of your core. So there will be a hydrogen shell burning layer. And also in the core, if the core is massive enough and contracts enough, then the temperature there will be high enough so that helium will start to fuse and you will get into the helium core burning stage, which will be when your star becomes a red giant, for example. So if our sun is in that stage, then it will be a red giant. It will be bloated a lot because of this hydrogen shell burning layer, which produces a lot of energy. So the sun will expand a lot. It will eat up all the planets, including, well, not all the planets. It will eat up all the planets up to Earth and eat up Earth as well. And I think just not until Mars, something like that. And then our star is a red giant, at which it will shed its outer envelopes, and then it at the very end just remain as like a white dwarf.
Okay, so thank you very much, Matthias. That was the shortest lecture on cell evolution I ever heard. Yeah, very good. Yeah. Okay, now more serious. The original word of thesis is that it is kind of a proposition, a claim. Yeah. So, what is your main claim from your work? What are you proposing here?
I would say the main claim here is that the current stellar evolution models that we have, so the current one-dimensional stellar evolution models, have errors and uncertainties on them that are very large and that actually dominate all of the stellar modeling that we're doing with them. So the observational errors are, well, very small compared to these theoretical errors. So if we have some way to improve upon in the future, then it's, well, maybe a good thing to look at these theoretical errors and see how we can reduce those instead of, well, try to reduce the observational errors even further. I mean, reducing these observational errors is very good, and it's something that, of course, is also a good thing to strive towards. But the dominant thing that is currently like impeding us from doing better modeling is these theoretical uncertainties that are present.
Yeah, that is right. I would contradict you a little bit because I'm doing stellar models, and I have known that the models have deficits all along the way. And in particular, your supervisor, since I've known her, always told me that the models are wrong. Yeah, so that's not a big.
All models are wrong. Some are useful. That's
yeah, that's a good sentence. Yeah, that's right. Yeah. Okay, we want to learn from your results. Okay. Now, in particular, of course, about the core convection in your case, that's the main point that you investigated, and the core connected boundary mixing. Now, you observe at the present age in a certain situation now. Yeah. Okay. So you tell me what is happening right now, but I'm evolving a star from its birth to its end, basically. So I have to know how that physics behaves along that evolution, at least in the main sequence. What can I learn from your results?
You say that I'm telling you what is happening right now. That's actually not entirely true, because what I tell you is what is the cumulative effect of what has happened up till now. So everything that has happened up to the point where I look at are things that influence how the stellar structure looks like. But like this evolution might be different at the very start of the main sequence and halfway through the main sequence, but it's like this cumulative effect that we're looking at. And well, I can say, well, this is the best prescription that cumulatively over this time that it has evolved, reduces what has happened cumulatively in our star. So that's, yeah, I think an important distinction there.
Yeah.
It's in that sense a good thing to also try to look at, for example, time-dependent descriptions of convection. So these descriptions that I've had here are just, we take one prescription, we set a certain value for this parameter, and we let the star evolve throughout the whole main sequence just with this one parameter, and that's just what happens, right? But a thing that might be worthwhile to investigate, and it's something that I've been collaborating on in the past few months with some people, that's to see if we can derive a value for these parameters based on, like, for example, the properties of the stellar core itself, and say, well, if our convective core has these properties, then we would, for example, say that this is the size of our boundary mixing region as well. And in that sense, have not a free parameter that describes it, but a value that comes from within the model. And that then also evolves if the model evolves. So if the model changes and your core changes, then this value for your convective boundary mixing will also change based on that. And I think that's also a good way for future work on this, and then to think about it instead of just fixing one thing and saying it's the same throughout the whole evolution. That it can vary.
Your answer at the beginning was, of course, absolutely true. Yeah, we see the integrated effect. Yeah, so to get into more, say, details of this evolution over time, it would be useful, of course, to have the same star at different ages. Do you have in your sample of Kepler stars objects where you could define such a sample, where you say, okay, it's basically the same star, seeing it at different ages?
Well, yeah, the unfortunate thing is that stars live much longer than we humans do. So yeah, we have the same star with like 4 years apart. It's not going to do much.
No.
We could try to stake a star with a very similar, if not the same mass as another one, and look at both of them in different stages of their evolution. That's true. In the stars that I have looked at, they are similar in mass, but not quite the same, I would say. So the stars that I've investigated have all been around 3 to 4.5 solar masses, so around that area. But that's still like considerable difference if you see that it's like
that's fine. But let's assume they represent very well one star of a typical mass. Are these two stars, in terms of their nuclear evolution, basically their age, different, say at the beginning and in the intermediate phase of the main sequence? Because I just wonder that at the end, when you said you found different results for the temperature gradient and for the mixing, or for the mixed structure, and you basically said, okay, that's because the uncertainties are too large. One star is better observed than the other one. Would it also be possible that these are really in the physics, so basically the convective efficiency over time, if they are in different age situations?
Well, in that sense, yeah, maybe that the cumulative effect of one works better in the early stages, and the cumulative effect of the other works better in the late stages. That's true. That's something that might be. Another thing that could also be the case, of course, is that stars are also just different, and that not every star is the same. Well, I would say one of the things that I'm a bit cautious about is to make very general statements about like every star does this, because I've only looked at a handful of stars, but I've looked at them in a lot of detail. I know some other people doing similar work. For example, Mathias Michielsen, who has looked at a very large sample of stars and has done some statistical approximations to model 26 or so of them at once. And what she found is that there is actually quite a bit of variety from star to star, and that some stars will do one thing and other stars do another thing. So it might also be that there are things that we are not thinking, like effects that we're maybe not considering, that change something in our star that then translates into, one temperature gradient outperforms the other one.
Okay, now to come to the conclusion, I have one, very specific question. You also mentioned that the stars are rotating, and you gave number. You said 40% of the critical rotation. Now, rotation is also a three-dimensional thing. What does it mean if you say 40% of critical rotation? Is that at the equator? Is that an average? Does it tell us about the interior, or what is behind that number?
Right. So yeah, the number that was on my slides is the rotation rate near the stellar core, right? So it's because that's the region where our G modes are sensitive to. So it's the near core rotation rate. And this fraction of the critical rotation rates means that, I use the Rush critical rate. So that means that if we have 100%, then our star would be rotating so rapidly that it would just lose material, and it would not be like a star anymore, and gravity wouldn't be able to keep it together. So yeah, by representing this in a way of the Rush rate, and this Rush rate is then calculated based on what is the mass of our star and the radius of our star, so what would this velocity be?
Okay, good. And the last question now, since I'm completely convinced by your excellent thesis, it's fantastic work. I'm a poor modeler. I have to listen always to people telling me the models are wrong, the models are bad. Can you give me an advice what I can do better?
It might be useful if I look at your models to be able to say that. So it's a bit difficult, but in general, I would say some general advice if you're doing stellar modeling is to, because it's something that I noticed with some other people, that sometimes gets overlooked, is to make sure that your not only your physics is something that you take care about, but also your numerics that go into your stars. Because, well, we're still doing a computer simulation of the star, and if you're doing a computer simulation, then you need to make decisions on, like, how are you gonna divide your stars into like cells that we make a computation for, and how big are the time steps that we take. And these are things that you should set with great care and consideration, and like try to see if you, for example, do a resolution study to see like, okay, well, what precision do we need to get consistent results? So that's something that I would say is good to always keep in mind when doing stellar modeling.
Yeah, okay, that's what we're doing anyhow. It's the physics. That's what we have to improve. Yeah. Okay, good. Thank you very much, Matthias. And this ends my questions. Thank you.
Thank you.
Okay, thank you very much. Then we turn towards the committee.
Maybe you can turn on the microphone again.
Yeah. We can.
On the top. Yeah.
Then we can also members or you. First, if I can invite those to present this.
Yes, thank you. So I'm Mathias. So my first question is indeed building on some earlier questions, where in your chapter 2 or your chapter 3, you quantify the uncertainties in the models that we currently have and what the effects are on the to fit into the data. But my question is, as was also asked by Professor Townsend, could we also quantify what the effect is of the things we don't know? Now we model the things we do know, but can you quantify the uncertainty of the things we don't know?
Well, that's a good question. I haven't thought about it in detail yet. Well, you can, when you have 2 layers to design, you can investigate things that you say, well, I know that there are things about this aspect that I don't know, and then you can see if I just play around with this effect and how much does this change things. That's something that we do, and that's very possible. But on the other hand, there are also things that we don't know that we don't know. And that's much more difficult to then come up with a way to take those things into account.
So is there a comparison with the data? Is that a good way forward to quantify this uncertainty?
Well, maybe yes, in a sense that in certain, also for example, in some of these period spacing patterns, so the theoretical ones that I chose, they were like nice and flat, they were evolved in these nice periodic dips in the pattern. But the observational ones, they were not as totally as, they're completely different than the ones that I showed in theory. And you can then look at these and say, well, what are things that might cause these changes that, well, then have this outcome? And that way, you can go. So yeah, for example, some things that I know that are not in my nodes is like mode coupling between different nodes that can cause like a sudden change of 1 or 2 nodes in our pattern. But that I haven't included them all, so yeah, it's not necessarily taken into account.
Okay. Another question I want to ask is about your grid computations, which you didn't discuss in your presentation, so I'll just explain this to the benefit of the audience. So what Mathias is doing is that he has a grid of computations in the sense that he wants to know what the highest mountain is in a certain region, and he asks the map, like in this region, what is the height of this point, and then he takes like 100 points, what is the highest point. But in mathematics, we have the method of steepest descent, and this is a naive method. If you're on a mountain, you go the steepest way up, and then you end up in the highest mountain, right? And so why don't you use the method of the steepest descent in your work? You do a grid computation of maybe 10,000 models or even more, if I did the correct calculations. Yes. Isn't it more computationally efficient to do the steepest descent or steepest ascent?
Well, might be computationally more efficient. However, the problem with such approach is that you're then very prone to caught up in local minimum maximum. So you might have like one area where you say, okay, well, this area performs pretty good, and well, we should go in that direction. Actually, in the other direction, it's first like bit of a downslope, but then there is a very high upward slope where you have the actual results. So you would still need to compute quite a lot of models to then be not susceptible to these. Yeah, and then if you look at like, you need to, let's say, refine areas where you say, okay, well, now we found something there, we find it, we zoom in, we compute more models in this region. So that's something that's something looking at as well. But yeah, the way to amount is that I just took one very quick, and that's where I just searched it and put the models. And then all the correlation structure is always because you only very few models. You say, well, let's compute not 2 million, but let's only 1,000, and you don't have the whole correlation structure of everything that goes there. And that's one of the very important things that I have in my results as well, is that these correlations and these theoretical uncertainties are something that we cannot just ignore.
And there's an application of, for instance, genetic algorithms. Does that help in this respect? Because then you naturally pick out the different spread out localized maxima.
Well, I haven't looked into genetic algorithms to do that. I think it might help out a bit, but I'm still not sure if that will solve the issue with the whole correlation structure of your circuits, right? Because you still don't compute things in every area to have a full overview of what the correlation structure looks like.
Okay, yes, maybe a final question. Yes. Okay, final question is about your future work, which is in your thesis, and it brings me back to the third year defense when you were saying what your plans were for the future, and you said you wanted to visit, was it Leiden or Delft? I don't remember, but they have the Amuse code.
Yes.
Yes, and you wanted to do all that in the final year, and we told you.
Yeah, that was very I'm actually doing it in
Exactly. But have you made any progress in that since then? Since now the thesis is written, now you have plenty of time.
So I've put that project a bit on hold to like first focus on getting the thesis done and then everything in that aspect, right? So myself, I'm still the way that I've done it now is just I'm at the point where I can evolve a model in one dimension, put the structure in the 3 dimension, and then compute it from that point onwards, all like on the fly using these use codes. So that you don't have to write output and then read it afterwards and these things. I just haven't made the coupling it back to the one-dimensional code yet. But however, I still have 1 year of funding left, which I can use to continue working, and that's a project that certainly piques my interest, and that I will probably not just drop. And that's something that that's one of the prime things that I would continue working on.
Yes, great. I'm looking forward to that. Thank you.
Okay, thank you very much. And then I would like to give the floor to Dr. Bobby Bowman.
Hello, Mathias. Hello. I'm going to say congratulations first. So this was a pleasure to read your thesis. Very concise and very efficient work, I would say. I'm going to correct said earlier, for the benefit of the audience, because Mathias says he does similar things to other people. That's not true. Mathias is a world expert in what he does, and there's literally one person who can do what he does, and that is Mathias. So he's being far too modest, who's not in charge. So I have 2 broad questions. So not only have you done fantastic science, you've also developed a lot of tools which have great benefits not only people in Leuven, but also in the world, so you make all your tools accessible for people. But I want to think about pushing you outside of your main sequence 3 to 5 solar mass regime. So let's imagine, for example, I find a beautiful pre-main sequence slowly pulsating V star. What would you have to modify? Is it physics or numerics for your tools to now allow you to uncover the uncertainties in that particular part of stellar evolution?
I would say you would need to change a lot in the stellar, the models that you are computing, right? But the analysis tools that I have made to then take like the modeling methodology to take the uncertainties into account and to like balance fit quality and model complexity. Those are not linked to this particular problem that I was looking at. So that's something that should be applicable to other things as well. So there shouldn't be that much changes made to be able to model things as well.
Where would you put your time in terms of addressing the physics of that pre-main sequence phase? Because we calculate our models and they reach the main sequence, we say they're perfect, right?
Yes. So yeah, one thing I do is I do calculate models for the pre-main sequence as well. So I don't just assume a starting value and work from that. I do the pre-main sequence calculation as well. But well, those are well, as I was made aware of by a colleague, Thomas Heindel, who does work on pre-main sequence stars. When he showed me what the evolution of his pre-main sequence effects looked like, it was completely different than what I had in my models. Because one of the things that we took into account was that the pre-main sequence star can still accrete material. So if the star is forming, you have a cloud of gas, and you have like the center that starts to form a star, but it can still like accrete material, and there can still be more mass that gets put onto the star, making it grow as it already is evolving. And that is something that is not in my models. Which has a very significant impact on what is happening on the pre-main sequence, at least during the pre-main sequence. The good thing I would say is that it does, in the end, go towards a thing that is very similar to what I have. But so for the models that I have in the main sequence, it's not that much of an issue. That the way to get there is different, because where you end up, it's the same. But if you would be modeling a pre-main sequence star, then that's something that's very much different than a lot of different physics with all the equations and such that we need to take into account.
Okay, thank you. So my second question, instead of now going along or backwards of the dimension of age, I want to go up in mass. So in a couple of places in the thesis, you make a statement that all massive stars have, and I quote, considerable radiation and wind. So could you just define what considerable means and what's the impact of that? If you want to do astroseismology of massive stars, where should we put our attention in the forward seismic modeling, in your opinion?
Yes. So if you have a star, for example, 3-4 solar masses like I did, then you do have some stellar width, and there is some material being lost, but it's not that much. Compared to stars when you, for example, have 20 or 30 or even more solar masses, which are very, very massive. And there you will start your star with, for example, 30 solar masses, but by the time it's at the end of the main sequence, it will have lost a few solar masses already, and it will be well, that's something that for those stars is much more important. And in those stars, things that you could look at, for example, is right now when we calculate for gravity modes, we have two boundary conditions. We say, well, we have the stellar center and we have the surface, and our mode propagates in this this region. But for these very massive stars, you actually could maybe use different boundary conditions at your outer surface, because there you can say, for example, you can have things like mode leakage, where you like have leakage of energy, that the mode loses energy that goes into the stellar mode as well. And it's not just confined to this, from the center to the surface of the star.
Yeah, I agree. So thank you very much.
Okay, thank you, Dominic. The Professor asks.
Yes, well, I've had 4 long years or plus to ask you and bombard your questions. So usually as a promoter, I don't ask questions unless the candidate says something or shows something that I don't like. And I couldn't find something. So I'll address you a bit later today, but I won't bother you tonight. Thank you.
Well, you got lucky, Mathias. Since this is public defense, ladies and gentlemen, I also would like to give the opportunity to you to ask questions that you might have to Mathias. Is there anyone? Yes, please. Speak up loud, please.
Hey, Mathias. One of your last slides, you showed the error bars of your theoretical models, so time bars that did not understand.
Yes.
How did you get those?
The theoretical uncertainty. I see. So the question is, if I heard everything correctly, how do I get to these uncertainties that I showed here on these figures, both the theoretical ones and the observational ones? Right? Okay, I just theoretical. So these theoretical uncertainties that I have here are based on the correlation structure of our theoretical model grid. So from this whole model grid, I compute a correlation matrix, a variance covariance matrix, right? And the values that are shown here are the largest values in this variance covariance matrix. So what this variance covariance matrix is, you can think of it as you take every pulsation that we have in our observations, right? So for one of these, it's like 36, and we put them on one axis, on the other one we also have 36 of those, and we see how much, if one varies, does the other vary as well. Right? So the value that it would have with itself is just its error on its own mode. But then you can have it in such a pattern, and you have these dips and these bumps, that well, if you have a dip, then you would expect that the one next to it would also like move a bit, just because one is in a dip. So they are correlated a bit. And yeah, this variance covariance matrix is something that takes all of these correlations. The maximal values that I have from the matrix are shown here.
So you don't really know what is causing, you just know there's a correlation between things and not giving like what exactly is wrong?
Well, what exactly is wrong? If I think I may come with a good answer, but out of the blue, it's a tough question, I would say. But yeah, it's a very good question.
Okay, thank you. Any other question from the audience? I don't see any. That means that everything was very clear, Matthias.
That's also.
So, to discuss on that, the PhD committee will now withdraw for the deliberation. So, ladies and gentlemen, we will now withdraw and we will come back soon. So, please bear with us. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for granting doctoral degree in science, astronomy, and astrophysics. Mathias Michielsen has presented to the faculty his PhD thesis on the topic Forward Seismic Modeling of P-type stars. Impartial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics. And he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of a doctoral degree that are prescribed by the law and university regulations have been met. Therefore, on behalf of the Rector of the KU Leuven, I confer upon Mathias Michielsen the degree of Doctor in Science, Astronomy, and Astrophysics. I close the session. Congratulations. Thank you all. This closes the formal part of the session, so please take a seat. Mathias, I have two important documents for you. First one is your preliminary diploma. Please enjoy it. There's no such thing as a free lunch. So therefore, Mathias, you have to sign this document to just confirm that you got preliminary diploma. And within a couple of months, years, decades, you will get the official diploma. Thank you so much. Congratulations again. Now, we'll be very happy to give the floor to Connie as promoted, who will say words.
Thank you, Mr. Is Dr. Mathias zeggen? Meneer Dr. Michielsen. Het is altijd het privilege van de promotor. En dan moeten we de science eerst feliciteren. Na de chef. En Dominique heeft het van harte Michielsen. And in the spirit of Mathias' style, I will try to keep the lecture to the point. Okay. Your academic path actually got by a son, and I'm very, very happy that this is time. He was a postdoc at our institute of astronomy many, many years ago when Mathias was a bachelor's student. And his son actually introduced Mathias into the main acceleration course and into the gyro precision course as a bachelor's student. And I think Mathias, it's fair to say that's how I perceived it already at that time, and still today, that you fell in love with this course, right? I want to thank you for doing that. You have seen the result today, and I'm sure you are super proud.
If I may access, I just shook hands with Mathias a few minutes ago, and I was hoping that since day one that I saw you and you showed me that I was confident that this day would come. And for me, actually,
Yeah, so it's something that's really a long time ago, and so I follow these steps. Having said that, I think maybe can you pull up our two next, please? I think it's also appropriate for me now to thank Rich, because actually the gyrotation mode that was crucial for Mathias' research was implemented and defined by Rich Townsend. And for us, this is a critical course. Yeah? And Rich, I keep forgetting that I have to ask you for more stickers because I run out of them very fast. And for us, this is really an enjoyable tool to work with, and it's thanks to you. So I wanted to thank you for that, and not only for being during my discussion.
You are welcome.
I also want to thank actually Achim, who's on the screen, because Achim is our Scholar Revolution expert that I've known since long. And he has been very constructive in the discussions with Mathias. I think you agree with that, right? Very pleasant. This is a world expert, so you did well, Mathias, to defend yourself. And I want to thank Achim for one very specific thing, and that is that he's always the person who tells me that we should never ever put all our eggs in one cell revolution gold basket, because then we all make mistakes. And so, thank you, Achim, for all the advice last decade to me. A few less years matters, but still, the last discussions in the past few weeks. And thank you for also offering the community with alternative code, which I actually enjoyed also using about a decade ago. Right? But let me return to Mathias, because he's the actor of the day. And then we'll switch to another language. Okay, can I tell you the En nu is het dus het familie is gegeven als het afgewerkt wordt. Aan de familie en vrienden van Mathias. We hebben Mathias alleen een fantastische astrofysicus, die bevestigd werd door alle experten die we hebben. Maar ook echt wel een goede software. En dat is wat een grote liefde ook wel ligt. Software development is niet eens, maar Mathias is iemand die het ook niet, en dat vind ik heel belangrijk, voor de noden van de vakantie. En dat wil ik hier op mijn werk zetten. Want als er iets verbeterd valt, dan moet het gebeuren en dat is altijd. Kan altijd beter. Vooral dan heb ik ook dan is Mathias een concept. Nu, ik moet wel toegeven dat ik een voordeel heb, want die hoort mij in de gang van het recht over mij zit. En dan komt de binnenvlieg in mijn bril en niemand kan dat stellen natuurlijk. En mensen horen dat niet. Maar mijn vraag, dat is zelf, maar ook toch wel vaak met een boodschap van mij te doen. Die misschien net die stap is en dat is heel goed. En als groepsleider moet ik zeggen, dat is wel bijzonder gelukkig om zo'n boodschap te hebben. En wat wij denken, dat wij samen delen, is een groot gevoel voor inclusie en discretie van het welzijn van onze mensen in de groep. Zowel studenten als familie, als iedereen. En dus onze dagelijkse activiteiten van onze instituten zeker heel veel profijt hebben. En de familie in de zorg. We zijn daar een beetje belangrijk, ja, sterk maar ontvangen. Zo zijn wij. Mathias bij ons, dat hebben we ook wel gehoord, want hij is veel aspiranten zijn, en dat is toch een knap, veel aspiranten zijn, dus dat verdient ook niet. Daar wordt het 5% betaald, in plaats van de reguliere 4 jaar, maar we worden geen na te zo niet mogelijk. Dan maken we in de universiteit een loopbaan met studenten, dat is 30 aan de 9 vanaf vandaag, ja, het zal niet meer lastig worden. Was er perfect bij het parcours, de tijdlijn van partners. Dat is, dat is zo. Dat is misschien of een leuk. Dus die zoveelste koppel dat gemaakt hebt. En zie je? Maar verder is het niets dus. Dus wat ik geleerd heb, ook in de afgelopen weken, zeggen Mathias bouwt van drukke stad, veel lawaai, zoals we in Manhattan afgelopen maand. En dan hebben we op manier staan, alleen als ik niet. Wandelen en voelen in Central Park, dus in deze studie heb ik voor jou een idee gekocht, om je de komende te vieren en ik hoop dat je daar komende tijd rustig kan doen. Voor jou, sincere congratulations, Mathias, on your PhD. Thank you for all your contributions to the Institute, to our group, and really forward. You're still for a little while with us, that you don't disappear tomorrow. That's great for us. I wish you very best of luck on your future. Congratulations.
Thank you. All right. I also brought something for Connie because Connie always says, "Let's celebrate with adults." So Connie's a really big fan. Now, I have lots of different kinds of adults. So we'll see which one she enjoys most. There you go. In the meantime, I would like to thank the online audience for tuning in. Well, I'm going to say goodbye and see you soon. Right? Cheers.